In this video, we're going to begin our study of the symmetries of the square. So in order to do this as effectively as possible, we want to actually make it very concrete and cut out a square about this size and label it in exactly the way that I've indicated. So on one side, right front, in the upper left, put a 1, the upper right, put a 2, the lower left, put a 4, and the lower right, a 3. On the other side of the square, right back, and label the corners in a way that's consistent with the labeling on the front. So for example, if I pull back this edge, you can see it was labeled 2, so I'm going to label it 2 here. On the other side, it was a 1, so it's going to be a 1 here. So everything should have the same number on both sides of that corner. You should also draw a picture like I have here. So if you look at your handouts for this unit, you should have one handout that has a picture that looks like this. So all I've done here is I've taken my square, I've traced it, and then I've drawn in a vertical axis, a horizontal axis, a diagonal axis, which I call D1, and another diagonal axis, which I call D2. So it's very important also that these are labeled in exactly the way that I've indicated here. So the vertical axis is V, this diagonal axis is D1, this one is H, and then D2. Okay? So all this labeling is just a convention. We could have labeled it in another way, but we want to focus on the mathematics. We don't want to get bogged down with notation. So if we all use the same notation, then we will always know that if there's a problem or discrepancy, that there's some mathematical issue and not just some issue with labeling. So it's very important that you label it in exactly this way, or else you're going to have a lot of confusion. So now the square is an example of what we called in the last lesson a dihedral rosette. In particular, it's what we called D4. So remember that a dihedral rosette is a geometric figure having only rotational symmetries and reflection symmetries. And so it turned out with a dihedral rosette that it had the same number of reflection symmetries as it had rotational symmetries. The square ends up having 4 rotational symmetries, and so it has 4 reflection symmetries for a total of 8. So in this lesson, we want to really understand the symmetries of the square in order so that we can see if we take 2 symmetries and we combine them together, we're going to get a new symmetry. It turns out that this will have a lot of properties that should resemble properties that you're familiar with from arithmetic, namely when you have real numbers or integers and you multiply them or add them, that those operations satisfied certain very nice properties. We're going to see similar properties when we do the symmetries of a square or the symmetries of a triangle or other types of figures, and that's going to lead into our study of groups. But before we can get there, let's go through the 8 symmetries of the square. So first of all, you have rotational symmetries. The first one is the one that's a little bit odd. It's what's called the identity symmetry. So right now, you want to always start with the square in this position, right? So it should say front, right? And 1 should be here, 2 should be here, and so on. It should look exactly like this. This is the starting position or the default position, so you always want to start in this. So now I'm going to do the identity symmetry for you. Did you see that? That's it. It seems kind of strange, but the identity symmetry simply means do nothing. You just stare at it. You don't actually move it. Right? So, as I said, it seems kind of strange to have such a symmetry, but a little bit later on, when we start talking about how to combine 2 symmetries, we'll see why the identity symmetry plays such a crucial role if we want to try to do, if we want to look at the algebraic structure of the collection of symmetries of the square. Now note that there's other ways that we could get the same effect. Right? So for example, actually before I get to that, let's consider the other rotational symmetries. So we had the identity symmetry, and now another thing I can consider is this. Right? I can put it back there. That's 90-degree clockwise rotation, right? I rotated it 90 degrees clockwise. So now when I'm looking at these symmetries, it's important to realize that I'm considering symmetries of the unlabeled square. It's pretty clear to see that if I take it and I do that 90-degree rotation, it looks a little bit different, right? Here you can easily read the word front because it's, it's laid out the right way. And here it's on its side. Right? But those labels are just ways for us to keep track of what's happening. Right? When we're talking about the symmetries of the square, we're talking about the symmetries of the unlabeled square. Namely, forget there was a 1 or a 2 or a 4 or a 3 or the word front. There's no features. There's just the set of points of the square. That's what we're talking about when we're talking about the symmetries. We're talking about transformations, rigid motions of the plane that take that square, move it around in some fashion, and make it look exactly the same way as when we started. Right? But so the labels will just be for our use, so we can kind of see what, when we do a certain symmetry, what has happened, which points have moved where. So that's 90-degree rotation, clockwise. We could also choose to do that counterclockwise. It won't make any difference. We just want to choose a consistent way of talking about all our rotations. So I'm always going to talk about clockwise rotations. You could just as easily talk about all counterclockwise rotations. Again, it's just a convention, but once we've chosen this convention, we want to stick to it so that we're not confused by different ways of labeling things. There's also 180-degree rotation clockwise. So here we do 90, and then we do 90 again. Right? And so now we can see the square is essentially upside down. Right? So we always return our square back to its starting position, because what we're trying to do is see from the starting position what happens to it when you apply one of these symmetries. So another possibility is 270-degree clockwise rotation. So we rotate it by 90, we rotate it by 90 again, now we're 180, and we do it once more, so there's 270-degree rotation. That's what it ends up looking like. Right? And now you could say, well, we could also do, what about 360-degree rotation clockwise? Well, what would that look like? There's 90, there's 180, there's 270, and there's 360. So notice what this looks like. This is our original position, our starting position or default position. And this looks the same as the identity. Now you might say, well, it doesn't look the same as the identity. In the identity, you just stared at the square, whereas in 360-degree rotation, you actually moved it a full cycle. But when we're studying these symmetries, it's important to emphasize that all we care about are the starting position and the ending position, and that's it. We don't care what crazy stuff goes on in the meantime. The point of a symmetry is, what does it do from the starting position? What does it do to the square? Where does it move the points? And so how it does that, we don't care. So if I just stare at the square, namely the identity symmetry, versus I rotate it 360 degrees, the end result is exactly the same. They look exactly the same, and that's why we're going to consider them to be the same. So the identity symmetry and 360-degree rotation, we will consider to be the same symmetry because the end result is indistinguishable. Namely, you could imagine if you looked away from the camera and I did 360-degree rotation and you looked back once I was done, you wouldn't know that I had done anything, and that's the point. Okay? So we've gone through our 4 rotational symmetries, right? Identity, 90-degree clockwise, 180-degree clockwise rotation, and 270-degree clockwise rotation. What about reflections? Well, that's why I have these reflections drawn on in the background. They help us see what's going on. So suppose I do, so let's actually start with V, vertical reflection. So remember, in a reflection, it fixes the points on the axis of reflection. So all these points here along V should stay in the same place. So what we're going to do is basically pick it up and put it back down. Right, so remember that reflections are what we called improper motions. So we have to actually pick up the geometric figure and put it back down in the plane. And that's the result. Right? So you should think that those points along that axis of V really haven't moved. They've stayed in the same place. But what's happened is basically we flipped. Right? So for example, here you had 1 and 4 on this side, and once we do that vertical reflection, now they're on the opposite side. Right? So that's vertical reflection. Let's go back to our starting position. What about horizontal reflection? So here, all the points along that axis are going to stay fixed, and we're going to pick it up, and now we're going to move it this way. Right? So that's the end result of horizontal reflection. So notice that 1 and 2 were up here, and now when I do horizontal reflection, they end up here at the bottom. Okay. What about diagonal reflection, D1? So right, notice that D1 goes through the points 2 and 4, right? These two corners, labeled 2 and labeled 4. It goes through. So in particular, those two corners should get fixed because they're on the axis of reflection. So if we do the reflection D1, they can't move. They must still be here. And so when you're doing this, you're going to kind of pick this up, and it's going to look like this, right? Notice that 2 and 4 are still in the same positions they were beginning. 2 was here originally, and 4 was here, and they're still in the same exact positions. On the other hand, 1 was up here, and now we see 3, and 3 was down here, and now we see 1. So they've changed positions. So let's do that reflection again. Right? And we get back. Okay, so that's D1. What about D2? D2 is right here. We can see that that axis of reflection goes through the corner labeled 3 and the corner labeled 1. So again, those two corners are going to be fixed. They're not going to be able to move. They have to stay right where they are. And so when we do this reflection, if I can actually get it here, it's going to look like this, right? Again, notice that 1 is in the exact same place it was before, 3 is in the exact same place it was before, but what has happened is that 2 was here, and now it's down here, and that 4 has also changed. 2 and 4 basically have switched spots. So let's do it one more time, and there we are, back to the beginning, right? So it's very important that you kind of make this drawing because these axes of reflection, this V, H, D1, and D2, you want to think of them as in the background. They are always in the same place. As you're moving your square and doing different rotations, reflections, whatever you're doing, they don't move. They're always in the background, in the same fixed position. So that's why it helps if you actually draw the picture like that.